Okay, today I'm going to look at a CTL series motor controller from Navitas. Now this is as far as I know, a discontinued product, and I think I know why, but it was a controller from a local school that the students had hooked up, I believe, in reverse polarity. So they smoked the bridge and the diode that was used for the freewheel. So I've torn this apart already, and the controller itself, there isn't really that much to it. If we actually look at it, we can see that there is main power board, so our B plus and B minus come in. They've got a set of caps sandwiched between two rails of a heatsink. This heatsink itself is live, so that's, I don't really like that too much, but that's the way they chose to do it. The second thing I don't like, so these FETs on this side and these FETs on this side are all connected, so that is one switch. So this is a low side switch. And something else I don't like about what they did here was that you can see that there's a bunch of screws that are actually holding the MOSFETs in. Now this is a known bad thing to do. Like, you don't do this because it bends the heat spreader of the TO220. So you don't actually get a proper flat connection between that heat spreader and whatever heatsink you're attached to. In higher end controllers, they will actually put a spring clamp of some sort that puts an even distribution of pressure across the face of the device. So that pushes the full heat spreader nicely across the heatsink that you're going to, so you don't get any point contacts forming and hot spots forming. The second thing that I noted when I took this apart, so there is two custom-made diode assemblies, and they're using I think 25 amp button diodes. Well, actually, maybe it wouldn't be 25, sorry, 100 amp button diodes, maybe higher, not sure. But what I did notice was that on the one that was blown, so one of these was used for plug breaking and one is used for the freewheel. When the low side switch turns off, the inductive energy gets spun around through the freewheel diode. So this guy had actually been overheated and unsoldered. At least I think it unsoldered. It could have been a defect of the part when it was actually assembled, because when I actually look at the diodes that are in this pack, the ones that were unsoldered, you just barely see it, they actually are okay, these two diodes. The three that are sandwiched still and soldered are blown. So they're blowing short. That's kind of a typical failure mode for silicon diodes and MOSFETs. So I'm not sure if this failed because we lost two diodes, which then put too much current through the remaining three. Diodes are really hard to parallel. They're a negative temperature coefficient, so what happens is as the device gets hotter and hotter, its forward voltage goes lower and lower and starts sucking more and more current. So that's why they have it on a copper conductor, soldered to the conductor, because this is also a really good low resistance for heat flow, and that's one way of them keeping all the diode dies at the same temperature. However, if you lose two and that current gets shunted through the other three, it's probably not going to last long. So this guy is the freewheel, and it's blown. So I'm going to, when I go to repair this, I'm not going to bother fixing this one. I'm just going to swap it with the plug diode version, and it looks like everything is soldered okay. And the school is not using the actual plug feature. They've got a permanent magnet motor attached to this thing, not a series wound. So I can safely toss this away. So another fun thing, I took a look at the control board, and boy, is it old school. This thing is all analog. There's no smarts on it at all. Got to be dirt cheap as well. Myself, don't like it, but you know, I'm not going to touch anything on the pots or anything from how they set it up, and hopefully it'll be fine. I did check that the totem pole driver for the low side MOSFET is still looking okay. Now this is a 12 volt unit, and the teacher had mentioned that he believed that this was over voltage with 24 volts. I don't think that actually happened. I think they just reversed connected it, you know, B plus B minus swap, because of the way the failure is that the freewheel diode and the bridge were failed, and these guys here are probably, you know, decent sized voltage rated, so I doubt that it would be over voltage from this. If they blew the bridge, that would not cause the freewheel diode to fail. So you had to have significant current flow going through it to cause it to fail. So that's actually good news. So the next thing I'm going to be doing is I have to work my way through. Like they went and silicon in all the caps, and for me to get that out is going to be hellish. So I'm going to try and replace these one at a time by unsoldering the leads, pulling them out, reapplying the silicon grease, and then, you know, hopefully after all of them are replaced and the dial's back in place, and I get the control board back in place, this will power up okay. I was really hoping that I could tell what the voltage rating of the caps were, because one of the requests was to be able to get this thing to run off of 24 volts. And if the caps were rated for that, the FETs were 60 volt FETs, I believe, or 55, 60 volt FETs. So that wasn't a problem. But the control card, I believe, is missing the ability to down convert 24 to 12. So they need 12 to run it. So one of the things I would say is if the caps were rated above, let's say 25 to, well, they wouldn't be 25 volts, but 50 volt caps, then it'd be a simple matter of just putting a down converter to 5 volts, like a DC down converter to 5 volts, and then doing a boost up to 12, so that they can then run this on either 12 or 24. But you know, that's a TBD thing. I don't know if I'm going to do it or not. I guess the first thing is to get it together and make sure it actually works. So, and with that note, I'm going to continue on and try and get back together. These FETs are definitely okay. All right, we will put those away as some backups and continue on with just replacing them with the new ones and reinstalling the control board and see what happens. So I did find out that it looks like it's 63 volt caps that they use in this thing. So in theory, we could build this up to be a 24 volt controller relatively easily, with a small mod. Now all the FETs have been replaced. So the original FETs were actually okay, and there must have been a short that I did not see when I was checking for a failed bridge. So I did replace the MOSFETs with new ones, and because I don't know what sort of abuse they've taken anyways by the students. I had to take the control board off several times. So the control board itself actually had some major issues with it. It had failed a PNP transistor that was used as part of the key circuit, or the key turn on, enable, off circuit. And that is used to enable an LM317 linear regulator, which supplies the 5 volts for various comparators and op amps on there, as well as the 5 volts for the external pot. In the meantime, taking this on and off has ripped some of the pads off. So unfortunately, I had to do some wire mods to kind of make the connections again. In addition, the gate driver, so when they put the gate driver transistors in there, they stressed the pins pretty badly by bending them at a certain angle. So they're very, very fragile, and the turn-off PNP transistor for the gate driver had broken loose. So I had to replace it with the next best thing that I had around. And unfortunately, it wasn't an exact pin or package, so it was kind of tilted over. So I had all this working, and then I put it together, and then I forgot to put the thermistor, which is tied to the aluminum heatsink underneath, right underneath the board. So then I had to take it off and then ripped off the pads and the through plating for where the 100 thou headers go through to connect the control board to the power base. So I've got it all together now, and it is functional. It turns on. The PWM goes up to 100% and all the way down to 0 nicely. So I have no way to really load this down to test it, so I'm going to put it back together and hand it off to the school to try in their electric car. And that's going to require me to reassemble this back the way it was. And that means that I'm going to have to make sure that the aluminum base is properly insulated with the original insulation material that was there. And then I'm going to have to figure a way to make sure I can cover up the screws that secure this aluminum base to the outer housing. They had used epoxy originally, which I chipped away, and that needs to be replaced with something that's insulative and won't allow students to accidentally short it out. So yeah, so that completes this. It is, as I had said in the earlier part of this, it's a horrible design. And to me, when I was going through the control board, there didn't seem to be any rhyme or reason to trace whiffs, and how things were routed it was just a mess. It was almost like an auto router had done it, but less so. So would I recommend you use one of these things? No, but if that's all you have, then sure. It's better than nothing. It does work with the way it's supposed to. It's just not a very efficient controller and not very robust. But then again, I mean, we are in 2022, and the digital world is upon us, and it's time to say goodbye to our old analog world, I think. Thanks for watching.